Welcome back, DeepVisus explorers, to Where Vision Meets Depth. Today, we delve into the fascinating realm of computing, inspired by the intricate architecture of the brain. In this episode, our journey is guided by the work titled Neuromorphic Computing, a theoretical framework for time, space, and energy scaling, published by James B. Aimone in 2025. For decades, traditional computers, based on what's known as the von Neumann architecture, have reigned supreme. Think of your everyday central processing unit, CPU, or graphics processing unit, GPU. They separate processing from memory, constantly moving data back and forth. This has worked remarkably well, but as we push the boundaries of computation, especially with complex tasks like artificial intelligence, we hit some fundamental roadblocks, primarily in terms of power consumption and efficiency. This brings us to our central question for today. How does neuromorphic computing fundamentally differ from conventional computing? And for what types of problems does it offer a significant advantage? Let's break this down. Neuromorphic computing, or NMC, is a radically different approach. Instead of separating memory and processing, NMC integrates them much like the human brain. Imagine each processing element, a neuron, having its own local memory, the synapses, directly co-located. This fundamental shift has profound implications for how these systems handle information. In a conventional von Neumann system, a program is a series of instructions stored in memory, and the processor fetches these instructions one by one. This serial execution means that even if you have many processors, the overall speed is still limited by the need to move instructions and data. Think of it like a chef constantly running back and forth between the recipe book and the ingredients. This constant data movement is surprisingly energy intensive. The paper highlights that the majority of energy cost in modern computers comes from these memory accesses. Now, contrast this with NMC. The program in NMC isn't a sequential list of instructions. Instead, it's directly encoded in the structure of the neural circuit, the connections between neurons and synapses. This means that once programmed, an NMC system doesn't need to continuously retrieve instructions from external memory. This immediately cuts down on a substantial part of the energy cost found in conventional serial programs. The primary cost in NMC is the initial loading of this neural model. One of the key distinctions the paper emphasizes is that NMC is intrinsically parallel and asynchronous. Unlike conventional parallel systems that often distribute primarily serial workloads across processors, NMC views every neuron as acting independently and asynchronously. This is a multiple instruction, multiple data, MIMD architecture, where different parts of the computation can happen simultaneously and without strict timing coordination. This stands in contrast to many graphics processing units, or GPUs, which excel at single instruction, multiple data SIMD tasks, like linear algebra, where the same operation is applied to many pieces of data simultaneously. The paper argues that NMC thrives in heterogeneous settings, where the computation lacks the uniform structure that SIMD architectures favor. Furthermore, NMC leverages spiking, an event-driven communication method where neurons only communicate if certain conditions are met, such as crossing a threshold. This minimizes communication costs, especially when many neurons are inactive, making sparsity a critical feature for algorithm design in NMC. This event-driven nature also means that time itself can be a computational element, not just something to be optimized away. Let's look at the theoretical metrics: time, space, and energy. From a time perspective, an ideal NMC architecture can execute any conventional algorithm at its minimal computational depth, meaning it should be as fast as or faster than conventional architectures from a time complexity standpoint. This is because NMC effectively dedicates a processing resource to every step of the program. However, the space requirements are different. Conventional architectures have a relatively constant space cost for processors plus the memory for the program and data. For NMC, the space required can scale with the overall size of the algorithm graph itself, meaning that in the worst case, every operation has to be physically realized in the hardware. This might seem like a disadvantage, but the paper points out that this spatial cost can be optimized through recurrence, reusing the same neuron resources for repeated computations, which is common in biological neural circuits. Now, for energy, this is where NMC really stands out. In conventional systems, energy is proportional to the total work, meaning every operation, regardless of whether it changes the state of a bit, consumes energy. In NMC, because processing elements are not shared and updates are event-driven, energy is proportional to the cumulative change of state. If an operation doesn't result in a change, no energy is expended. This means that algorithms that exhibit sparsity or converge to a steady state, leading to fewer changes, can see significant energy savings. So, to answer our central question, neuromorphic computing fundamentally differs from conventional computing by integrating processing and memory, operating with intrinsic parallelism and asynchronous event-driven communication, and tying energy consumption to the actual change in computational state rather than absolute work. For what types of problems does it offer a significant advantage? The paper identifies several classes. Recursive algorithms, those where the computational graph can be described with cycles, allowing the reuse of neuron resources, which lower spatial cost and communication penalties. Iterative optimization algorithms. These are algorithms that converge on a solution over time. As the algorithm approaches its solution, the activity in the neuromorphic system would decrease, leading to significant energy savings. Probabilistic algorithms and large-scale sampling, such as Monte Carlo simulations, where the ability to efficiently handle sparsity and the event-driven nature of NMC can provide advantages. Heterogeneous computational graphs. Unlike SIMD architectures that prefer highly structured problems, NMC thrives where the computations are diverse and less uniform. Graph algorithms. The paper highlights provable advantages for certain graph algorithms in spiking neural networks. In essence, while conventional systems, especially GPUs, are optimized for dense numerical applications like linear algebra, NMC is ideally suited for scalable and sparse algorithms whose activity is proportional to an objective function. As we close this chapter, remember that the quest for true intelligence, whether biological or artificial, is an unending symphony of discovery. Join us next time on DeepVisus as we tune into another frequency of the brain, mind, and intelligence, unraveling the mysteries that shape our understanding of thought itself.